10.3. The integral test. The outline of this video is as follows. We will begin by introducing the integral test, a powerful method for determining whether an infinite series converges or diverges by comparing it to an improper integral. Next, we will apply this test to a special and very important type of series called the p-series, which will lead to a simple rule for its convergence. Finally, we will learn how to use the integral test to estimate the error, or remainder, when we approximate the full sum of a series using a finite number of its terms. This will allow us to understand the accuracy of our approximations. We will now focus on a special but very important type of series, one where all of the terms are non-negative. This condition simplifies the question of convergence a great deal. Consider a series where every term a sub n is greater than or equal to 0. The sequence of partial sums, s sub n, is formed by adding these terms one by one. Since we are always adding a non-negative value, each partial sum must be greater than or equal to the one before it. This means the sequence of partial sums is non-decreasing. From our study of sequences, we know that a non-decreasing sequence has only two possible fates. It either grows without limit toward infinity, or it converges to a finite value. The monotonic sequence theorem tells us that it converges precisely when the sequence is bounded from above, meaning there is some ceiling value that the sums never cross. Therefore, we arrive at a powerful conclusion for these series. A series of non-negative terms converges if and only if its sequence of partial sums is bounded from above. Let us examine a classic and important counterexample called the harmonic series, which shows why the terms of a T-series approaching 0 is not enough to guarantee convergence. The harmonic series is the sum from n equals 1 to infinity of the fraction 1 over n, that is, 1 plus 1/2, plus 1/3, and so on. Although the terms 1 over n do go to 0, the series actually diverges. We can prove this by showing that its partial sums are unbounded. The key is to group the terms in a specific way. For instance, the sum of 1/3 and 1/4 is greater than 1/2. Likewise, the sum of the next four terms, from 1/5 through 1/8, is also greater than 1/2. We can continue forming these groups of terms indefinitely, and the sum of each new group will always be greater than 1/2. Since we can add an infinite number of these groups, each contributing more than 1/2 to the total, the partial sums will grow without any upper bound. Therefore, the harmonic series diverges. The integral test provides a powerful way to determine if a series converges by comparing it to a related improper integral. The core idea is to treat the series terms a sub n as values of a continuous function f of x, and then visualize these terms as the areas of rectangles under the function's curves. Let us apply this to the series that sums the quantity 1 over n squared. Here, our function is f of x equals 1 over x squared. As the diagram on the slide illustrates, the partial sum is the total area of the rectangles. This area is bounded above by the area of the first rectangle, which is 1, plus the area under the curve from x equals 1 to infinity. We know from our study of improper integrals that the integral of 1 over x squared from 1 to infinity converges to a value of 1. Therefore, any partial sum of the series will be less than 1 plus 1, which equals 2. Because the sequence of partial sums is increasing and is always less than 2, the series must converge. This figure provides the key visual insight for a powerful method called the integral test. Here, we are testing the convergence of the series whose terms are 1 over n squared. The smooth, red curve is the graph of the related continuous function, f of x equals 1 over x squared. The terms of our series, a sub n, are simply the value of this function at each positive integer n. Notice the blue rectangles drawn under the curve, starting from x equals 1. The height of each rectangle corresponds to a term in the series, such as 1 over 1 squared, 1 over 2 squared, and so on. Because every rectangle lies entirely underneath the curve, the total sum of their areas must be less than the total area under the curve. We can find this total area by calculating an improper integral. Since the integral of 1 over x squared from 1 to infinity converges to a finite number, it provides an upper bound for our series sums. This visual argument shows that if the integral converges, the corresponding series must also converge. This slide formally states the integral test, a powerful tool for determining if a series converges, and it highlights a critical caution. The test says that if you have a series with positive terms, and you can match those terms to a function that is continuous, positive, and decreasing, then the series and the corresponding improper integral behave the same way. That is, they either both converge or both diverge. Now for the crucial warning. The test only tells you about the convergence behavior. It does not say that the series and the integral converge to the same value. This is a very common point of confusion. For example, we know the series given by the sum of 1 over n squared converges. The integral we use to test it, the integral of 1 over x squared from 1 to infinity, evaluates to exactly 1. However, the actual sum of the series is not 1, it is a different number. The essential takeaway is that the integral test determines convergence or divergence, but it does not calculate the sum of the series. The proof of the integral test works by trapping the partial sum of the series between the values of two closely related integrals. By visualizing the terms of the series as the areas of rectangles with a width of 1, we can establish a crucial inequality. The total area of these rectangles, which is the partial sum s sub n, can be shown to be greater than the integral of f of x from 1 to n plus 1, but less than the first term, a sub 1, plus the integral from 1 to n. This inequality is the engine of the proof. If the improper integral from 1 to infinity converges to a finite value, the right-hand side of the inequality proves that the partial sums are bounded above. Since the terms are positive, the partial sums are non-decreasing, so the series must converge. On the other hand, if the integral diverges to infinity, the left-hand side forces the partial sums to also grow without bound, meaning the series diverges. Therefore, the series and the integral must share the same fate. They either both converge or they both diverge. We can now use the integral test to establish a simple rule for a very important family of series called p-series. A p-series is any series of the form, the sum of 1 over n to the power p, where the exponent p is a fixed real constant. The key insight is that this series corresponds to the function f of x equals 1 over x to the power p. From our study of improper integrals, we already know the behavior of this function. The integral from 1 to infinity of 1 over x to the p converges only when p is strictly greater than 1. It diverges for all other values, that is, when p is less than or equal to 1. By the integral test, the series must behave in exactly the same way as the integral. This gives us the p-series test. The series converges if the exponent p is greater than 1, and it diverges if p is less than or equal to 1. For example, the harmonic series, where p equals 1, diverges. But the series 1 over n squared, where p equals 2, converges. The integral test is powerful because it not only confirms convergence, but also let us estimate the error when we approximate an infinite series with a finite partial sum. When we use a partial sum, s sub n, to estimate the total sum, s, the part we are leaving out is called the remainder, r sub n. This remainder is the sum of all the terms from a sub n plus 1 onward. We can trap the value of this remainder between two integrals using the same function, f of x, from the test itself. Specifically, the remainder r sub n is greater than or equal to the integral of f of x from n plus 1 to infinity. At the same time, it is less than or equal to the integral of f of x from n to infinity. This gives us a firm upper and lower bound on our error. By adding our calculated partial sum, s sub n, to all parts of this inequality, we get a new set of bounds that trap the true total sum, s. These inequalities provide a practical way to determine the accuracy of our partial sum approximation. This slide provides the key visual proof for the remainder bounds we just discussed, using a continuous, positive, and decreasing function f of x to represent our convergent series. The remainder, r sub n, represents the sum of all terms from a sub n plus 1 out to infinity. First, consider the upper bound illustration by drawing rectangles between n and n plus 1, where the height is determined by the function value at the right endpoint. We represent the terms of the remainder, starting with a sub n plus 1. Because these inscribed rectangles lie entirely under the curve, their total area is less than the area under the curve from n to infinity. This confirms that r sub n is less than or equal to the integral of f of x from n to infinity. Now look at the lower bound illustration. If we shift the rectangles so that each height is determined by the left endpoint starting at n plus 1, the rectangles are now circumscribed over the curve. In this configuration, the area under the curve from n plus 1 to infinity is entirely contained within the rectangles. This visually demonstrates that the remainder r sub n must be at least as large as the integral of f of x from n plus 1 to infinity. By trapping the remainder between these two integrals, we gain precise control over the error of our approximation. Let us now apply the remainder bounds we just developed to estimate the true sum of a familiar convergent series. This example shows how the integral test gives us a practical tool for approximating an infinite sum with a known level of accuracy. We will estimate the sum of the series 1 over n squared using the partial sum of its first 10 terms, denoted S10. The bounding inequalities from the previous slide require us to evaluate an improper integral. For our function, f of x equals 1 over x squared, the integral from n to infinity is simply 1 over n. Applying this for n equals 10, the formula tells us that the true sum s lies between s10 plus the integral from 11 to infinity and s10 plus the integral from 10 to infinity. This means s is trapped between s10 plus 1/11th and s10 plus 1/10th. Using the given value for S10, we calculate the final numerical interval shown on the slide. The key result is that we have trapped the exact value of the infinite sum within a very narrow window, between approximately 1.640 and 1.650. Let us summarize the main ideas from this section on the integral test. We began with the fundamental condition for a series with non-negative terms to converge. Its sequence of partial sums must be bounded from above. The integral test gives us a powerful method to check for this. If the terms of a series can be described by a continuous, positive, and decreasing function, then the series and the corresponding improper integral will either both converge or both diverge. But a direct and very useful consequence of this is the p-series test. This provides a simple rule for any series of the form 1 over n to the power of p. The series converges if p is greater than 1 and diverges if p is less than or equal to 1. Finally, beyond just determining convergence, the integral test also provides a practical tool for estimating the sum of a series by giving us bounds on the remainder. In short, the integral test links discrete series to continuous integrals, providing a key tool for determining convergence and estimating sums. To wrap up, Let us consider two review questions that will help solidify your understanding of the integral test and its applications. The first question asks you to think critically about the conditions of the test. Why must the function f of x be positive, continuous, and decreasing? Consider what would happen to our area-based arguments if any one of these conditions were violated. For example, if the function were not always decreasing, would the rectangles still provide a reliable upper and lower bound for the integral's area? The second question is a practical problem you will often encounter. It asks you to use the remainder estimation formula. Specifically, you need to determine how many terms of the series, the sum from n equals 1 to infinity of 1 over n cubed, are required to approximate the total sum with an error no greater than 0.001. This involves setting up an inequality using the remainder bound we discussed. I encourage you to pause the video and work through these problems, as they are an excellent check on your understanding.